everybody. Today for our seminar, we're going to have Isabella Pretto from SXS talk about ring down in binary black hole simulations. So yeah.
Hi everyone. Thank you for coming to my talk. Wait, do we have control over or is it? Yes. Okay, so today I'm going to be talking about ring down in binary black hole simulations. I will start by explaining what ring down is, and then we're going to go a little bit into perturbation theory applied to black holes, and then I will talk about how my work, which is how do we even find Posner removes when looking at the ring down, and I'll explain what Posner removes are. So, as we know, when two black holes collide, the immediate product is a perturbed black hole, which becomes a stable black hole, a stable curved black hole by emitting gravitational waves in what is known as the ring down. And just to give some context, in 1957, that's when we can say that black hole perturbation theory, or the concept of black hole perturbation theory, was first introduced by Reggie and Wheeler when they were analyzing a specific kind of gravitational perturbation to the Schwarzschild metric. And that was, interestingly, even before Wheeler coined the term black hole. In '63, Kerr found the solutions for when you have a spinning black hole. And in 1971, other physicists such as Zarrilli, which were present days, expanded on the work to perturbation to the Schwarzschild metric that was first introduced by Reggie and Wheeler. So Zarrilli, for example, understood that you could decompose those perturbations in terms of what looked like oh, I forgot what's the name, guys, quantum mechanics. Schrodinger-like equations. Yes. Yes, and then there was some work that was further developed to extend those that initial analysis that was restricted to a certain kind of perturbation to general gravitational perturbations. And in 1973, my advisor, Sal Topolsky, managed to separate the perturbation equations. Yeah, it's good to say my advisor, right? Yeah, the perturbation equations in the Kerr metric by using the Newman-Penrose formalism. And then a couple of years later, Chandrasekhar and Wheeler numerically computed some of these characteristic frequencies, so particularly the least damped ones.
Did you know that was not even Saul's main PhD project?
Yeah.
He had something other that Kate gave to him.
Yeah.
And he was like just working on it as a side project, and he did, okay, wow, I did it.
And he did that his third year, right?
I mean, he graduated in 3 years, so you can actually look into his contact thesis in the web.
And became faculty right afterwards, so that sets the bar. Okay, so just some background when it comes to the Kerr metric. So the Kerr metric is the most general vacuum black hole solution in 4D asymptotically flat space-time. And what my advisor found was that when you use curvature invariance, the perturbation equations decouple and separate, which was what he achieved in early 70s. And that led to the development of the master perturbation equation for fields of general spin. So not only for gravitational fields, but also for electromagnetic and other scalar fields. And yeah. So that was entirely based on the Newman-Penrose formalism, which is itself based on the idea that you can have a tetrad of null vectors. So you assign a tetrad of null vectors to each point in space-time, and then you decompose your tensors in terms of these vectors. And the curvature variables that are most relevant here are the Weyl scalars, and which you can obtain by contracting the Weyl tensors with the legs of the tetrads. And these are the quantities that are relevant because they describe ingoing and outgoing waves. And psi4 in particular is the one that we are going to work with. Okay, so the idea is that, say that psi describes a spin as field. You can decompose decomposi in terms of spin-weighted spheroidal harmonics, and then Fourier transform that, obtaining this decomposition. And when you do that, you obtain the famous Tucholsky equation. So this is clearly very complicated, but the only thing that you should pay attention to is that when you are applying that to gravitational perturbations, your equations will depend only, or the Tucholsky operator will depend only on the mass and the spin of the black hole. And by applying that decomposition to the perturbation equations, my advisor found that this this two ODEs for the radial dependence and for the angular dependence. The solution to the first one is given in terms of spin-weighted spherical harmonics, and the solution to the second one is a little bit more complicated. But as I said, just remember that those depend on the mass and the spin of the remnant black hole. Yeah. Okay, so when we are talking about solving for those equations, first we need to impose physical boundary conditions. And the post-normal modes, they appear as a solution to those equations when you impose physical boundary conditions. So essentially that when you go to the horizon, you should not expect anything coming out. Classically, you should only expect waves coming in. And when you go to infinity, you should not expect any random waves, so only radiation going out. So that leads to these two conditions that in turn result in post-normal modes. And it is also important to say that post-normal modes do not form a complete basis. So you cannot describe the ring down, at least for turning perturbation theory entirely in terms of post-normal modes. Okay, so what do they look like? So after the prompt response, which is like the most nonlinear region right after the black holes collide, the post-normal modes dominate the waveform. Of course, you still have tails, parallel tails at the end, but those are not they're not the dominant contribution. The dominant contribution comes from post-normal modes, which are present at intermediate times in the ring down. And the idea is that you can decompose your strain in terms of a sum of damped sinusoids. So here, C is the complex amplitude. Omega gives you the complex frequency, and the important thing here is that the complex frequency depends only on the mass and spin of the final black hole. S is the spin-weighted spheroidal harmonic for spin weight -2, so gravitational perturbations. And A is the dimension-full spin of the black hole. And L and M are giving you the angular harmonic, or the angular harmonic numbers, and the overtone index. So N equals 0 gives you the longest lived mode. And P labels the retrograde, whether it's retrograde or prograde. I didn't write that here, but I can write that down. And we say that, well, we define P as the sine of M times the real part, of omega. And positive means prograde, negative means retrograde. So that's the labeling that we are going to use throughout this talk, and that we usually use in ring down work. Okay, so because the frequency, the complex frequency depends on the mass and the spin of the final black hole, if you can detect at least two frequencies, you can test the Noether theorem, which says that astrophysical black holes should be entirely described by their mass and spin because we ignore charge for astrophysical black holes. And yeah, so the idea is that you can measure these two frequencies, and if they are described by the same mass and same mass and spin, then that is consistent with GR. And if you find deviations from that, then well, good luck. Okay, so we are going to focus on the results from first-order perturbation theory, but I would just briefly go over what second-order perturbation looks like. So the idea is the same: is to have the same Tucholsky operator acting on the field, and you have a very complicated source function which vanishes when we're talking about linear perturbation, but is non-zero for second-order perturbation. The important thing about that source, the source term, is that it depends quadratically on the linear perturbation, and what that means is that LA times you can you find that the solutions are quadratic Poisson-Normal modes. The important thing about quadratic Poisson-Normal modes is that because there is this quadratic dependence on the first order perturbation, their characteristic frequency is given by the sum of the frequencies of the parent modes. So that's something that we will use later. And there is also results for third order perturbation theory, but those are more complicated. And again, the frequency is also given by the sum of the frequency of the three parent modes. Okay, so I just told you that we can, using first order perturbation theory, we can fit the ring down using a sum of damped sinusoids. So that seems to be a simple enough problem, right? So you could, if I were to ask you, okay, so how do I do that? You could probably say, well, maybe just some regular least squares fitting. But the issue is that it is an inherently ill-conditioned problem. So if we define the well-posedness of a problem in terms of there being one unique solution that is also stable, so what that means is that if you shift the input, you should expect by a little, you should expect your output to shift by just a little as well. Then your then fitting for QNMs is inherently ill-posed, and you can think about that. Well, there are many reasons why it is ill-posed. So, for example, you do not know a priori how many terms are there, so you cannot come up. So you cannot find a function that looks like this one to fit for. You also don't, if you want your fitting to be agnostic, you cannot use any mass or spin to fix the frequency parameters. So it is generally very hard to fit for QNMs. And you can also find many different modes that will give you an equally good fitting. So you also need to apply some physical intuition when you try to develop an algorithm that will do that fitting for you. Okay, so before I delve into the details of our algorithm, there are some ideas that I want to establish. So the first idea is that our algorithm is entirely based on the variable projection algorithm. And the idea for the variable projection algorithm is that, well, say that you have your, what? Sarah, do you have anything to say?
No,
about
I
bar
spent
pro?
a lot of time working
Bar
on
pro? Yeah, so the goal of variable projection algorithm, or bar pro, is to find an optimal solution for a separable nonlinear least squares problem. So the idea is that, say that you have a time series and then you want to fit that time series with a function that looks like this, where this is indicate your linear parameters, omega nonlinear parameters. And in our case, C will be the complex amplitude and omega will be the complex frequency, which we don't fix to anything because we want our fitting to be as agnostic as possible, as I said before. The idea is that you start by setting some initial guess to the nonlinear parameters. Then you're going to do your usual least squares fitting to find the linear parameters. Then fixing those linear parameters, you're going to optimize over you set the nonlinear free, then you optimize over the nonlinear, then you keep repeating this procedure until you reach some suitable tolerance. And that's how we optimize over both nonlinear parameters and linear parameters at the same time. Okay, so having established that this is how we do our fitting, the main idea of our algorithm is to find QNMs that are physically meaningful. So how to determine whether or not a QNM is physically meaningful if you can have different sets of QNMs that will fit the ring down equally well. You can think about that in terms of the stability. So whenever you go to talk about ring down, people will usually talk about the stability of QNM. So what does that effectively mean? So if you, from a data analysis perspective, so that you have your ring down and you are fitting for only one damped sinusoid. So the idea is that if you perform your fitting over different start times, you would, if a QNM is truly there, then you would expect the amplitude to decay as it would based on the damping time of that QNM. And if you find deviations from that that are not related, to noise or to the QNM having already decayed, then you shouldn't expect it to be true there. You should expect it to be modeling some non-QNM content. So to be more specific, the way we measure that is, well, wait, let me go back here. So the way there's a couple of approaches a couple of things that you can do here. So the idea being that you want to make sure that the amplitude measured from fitting times is tracking the expected decay from the QNM. You can think about extrapolating that amplitude to some reference time, which we usually set to be the peak of the strain or the peak of the news, or usually the peak of the luminosity flux. And then when you do that, you can look at the fractional variation of that complex amplitude that is extrapolated to this reference time. And we look at the variation of both the real and the imaginary parts. And we require that that variation is smaller than some fixed threshold over a time window, and this is important, that is related to the decay time of that QNM. And the reason why we do that is because you wouldn't expect, for example, a 2-2 fundamental that lives a really long time to be stable over the same time window as a 2-2-4, which is a short-lived mode. 2-2-4 should have already decayed by the time while 2-2-0 is still stable. So we really want that minimum time window to reflect the expected damping time of your QNM. So here we are essentially saying that your extrapolated amplitude shouldn't vary by more than some sigma max over a time window where the amplitude of your QNM decays by some factor. And it has been asked whether or not that approach makes sense, whether or not you could still be modeling some non-QNM content and find your amplitudes to be very stable, just because there could be some correlation between the QNM frequency and the non-QNM content. And what we found was that yes, it seems to be a very robust approach. And what I'm showing you here is the fitting start time with respect to the peak of the strain on the x-axis, and on the y-axis you have the extrapolated amplitude to the peak. So the first plot I am showing you, first I'm fitting here an analytic model that consists of all of the first 3 overtones plus this one quadratic mode. And what I'm showing you in the first plot is, what if instead of fitting that model with the correct quadratic mode, I fit it with one mode that is very close in frequency to the correct one? Will I be able to find variations in the amplitude? And the answer is yes. But the interesting thing is that you do not find variations in the extrapolated amplitude of that quadratic mode, but of the 2-2-3, because it is the mode that is closest to the quadratic mode in terms of decay time. So the variation that would come from that incorrect fitting will appear in the stability of modes that are close in frequency, generating this instability that you can see in the first plot. So in the second plot, you see what you would expect by fitting all of the modes correctly. So yes, even if you have 2 modes that are very close in frequency, which you can see there, you can still differentiate them based on the stability test. Okay, so how do we automate the search for QNMs and numerical relativity waveforms, given that it is not a trivial problem? So our main approach consists of fixing the end time of the ring down, and then we iteratively move the start time of our fitting while looking for free frequencies. Then we check to see whether those the corresponding modes are stable based on that stability criterion that I just defined. And if they are, then we add them to the model. We fix them in the model and continue the search until the peak of some quantity of interest. Okay, so that's the general idea. So now I'm going to delve into the details. Okay, so we, having fixed the end time of our fitting, which will stay the same throughout all of the iterations, we start with some fitting start time, which is usually, say, if our end time was 8 AM, then our fitting start time should be very close, so say 75 AM, the first fitting start time. Then because we are looking at the entire 2-sphere, instead of restricting ourselves to the 2-2 mode alone, we're going to look for the most unmodeled LM mode. And what that means is that we will check the power of the residual between the current QNM model, which when you're starting is none, and that mode in the string, and focus only on that harmonic, that specific harmonic. Then we are going to apply VARPRO, looking for only one frequency, and then if we see that that frequency that is given by VARPRO through the best fitting procedure is sufficiently close to the frequency of a QNM, so we are computing based on the mass and the spin of the remnant black holes, a set of possible QNMs, then we test whether or not that potential new QNM found is stable based on the stability literature that I just described. Then, if it is stable, then we add it to the model and change the start time to an earlier time, having again that end time of the fitting fixed, and then we repeat this procedure again. If it's not stable, then we try to increase the number of free frequencies that VARPRO is allowed to use, and then we perform the same fitting again. So there are some features of our algorithm that are very new in the literature and that allows our code to be very successful. And the main one is this issue with the iterative fitting. So the idea is that because you don't know how many QNMs you have a priori, you cannot, you could end up either overfitting terms or underfitting, which would make you lose even more terms, because essentially when you're fitting a bunch of damped sinusoids, if you miss the highly damped ones, you may also end up missing the ones that live longer just because of an issue with the stability, which I described earlier. So that's why it's super important to consider stability when you're talking, to consider the damping time when you're talking about stability. So when you do this iterative fitting, what you end up doing is you first find the long-lived modes, which gives you enough model stability to search for the short-lived modes. And that means that you end up finding more overtones and even quadratic terms close to the peak, where you would expect to have more of these terms and also nonlinear contributions. The other point is that we are fitting over multiple harmonics instead of only the 2-2. And the reason why that is important is because when you are looking at different BVH systems, you could end up having more power in different L's, not only the 2-2. The second reason why that is important is because that allows you to further restrict your search for QNMs in a way that is physical. So, and that is particularly true for quadratic QNMs. So for example, you wouldn't expect to have a quadratic term if you haven't found the parent modes in their original harmonics yet. And that is something you can only impose when you are looking at multiple harmonics as opposed to only the 2-2. And also the multi-frequency search. The multi-frequency search is very important when you get closer to the peak, because that's when you would expect many modes to have similar decay time. So if you're only looking for one mode, you would not be able to establish that mode as stable if it is decaying at a time that is too close to the decay of another mode, simply because that window that I showed you is too large to account for only one mode. And when you do this multi-frequency search, you can find even more overtones and modes closer to the peak. And the stability that I just showed you, usually in the literature people tend to fix the time window, which means you end up missing modes because, well, you cannot, as I said, expect a mode that decays fast to be stable over a window that is too long. And another issue with having a fixed window is that you may lose the statistical significance if you look at a window that is too short and introduce spurious terms. So you really want to look at a window that is related to the damping scale of the mode. And we validated our algorithm by testing a bunch of numerical waveforms that incorporate quadratic terms, retrograde, prograde modes, and higher harmonics over varying levels of both non-Gaussian and Gaussian noise. And that allowed us to find optimal values for those parameters that control the stability test, and also to validate our approach. And yeah, so now I'm gonna show the results that we got by applying that algorithm to actual numerical simulations. So here I'm showing you on the x-axis fitting start time with respect to the luminosity peak. So focusing first on the top plot, I'm showing you the amplitude as a function of start time for an equal-mass non-precessing system with anti-aligned spins. And the different colors labeled the different modes that were found in the order that they were found. The thicker line shows where the modes are most stable. And what you can see here is that we found the first two overtones of 2-2. We also found retrograde modes and a quadratic contribution, in addition to contributions in other harmonics. What you can see on the bottom plot are multiple measures of error. So black line is showing you the normed strain. Blue line is showing you the expected error from the expected numerical error. Pink one, the mismatch between the ring down and the numerical strain and the our QNM model. And the yellow is overlapping with the orange one, and that is showing you how our QNM model relates to the expected value of the strain. And well, what that is showing you is that at around 10 m, if you're constrained, if you're looking at the mismatch around 20 m, if you're looking at the yellow and the orange lines, our QNM model is already sufficiently accurate to or stable to model the ring down. Another one. Well, okay, so that was one specific example, but we also analyzed over 100 quasi-circular non-precessing systems with mass ratio less than 8 and spin of the black holes less than 0.8 to better understand how these QNMs are excited. So according to first order perturbation theory, your complex amplitude can be described in terms of a source function, which depends only on the source. It's a very complicated function that depends only on the source of perturbation, and the excitation factor that is independent of the source of perturbation. It is more of a quantity that shows how different QNMs are naturally excited. It was found recently that in addition to that, when talking about the relationship between the complex amplitude and the excitation factors, you also need to account for a time ambiguity that is related to the time that it takes for QNMs to be excited. And that allows us to redefine the relationship between those two quantities in this way. So by introducing this delta T naught, which is the time ambiguity factor. So if we want to invent, and the quantity that we want to investigate is the source function I, and also this time ambiguity factor as a function of overtone number. And that is because it's been suggested in the literature that source function might be independent of the overtone index. So that it is flat when you are looking for quasi-circular equal spin systems as a function of the overtone number for the 2-2 mode. And the way we investigate that is first by constraining those three parameters in terms, so delta T naught and I, in terms of the theoretical values predicted for the excitation factors of the 2-2 and its first overtone, and the measured amplitudes of the 2-2 and its first overtone. And effectively, what this means is that when we are looking for the relationship between the excitation factor and the complex amplitude of the 2-2 and the 2-2-1, they will be made to exactly match each other. So, well, yeah. Okay, so here I'm showing you the results of that analysis. So on the x-axis, the value of the remnant spin, on the y-axis, the amplitude of 2-2 and its first 3 overtones. So blue and green are only from 2-2, fundamental 2-2-1, so they are exactly the excitation factors and amplitudes are exactly matching each other because that's how we define things. So the real analysis happens for the for 2,2 and 2,2,3. So orange and pink. So the data points are showing you the extrapolated amplitude. The arrow bars is standard deviation, so 1 standard deviation over the window where that mode is most stable. And the curve, the solid curve, the value of the excitation factors. So what that is showing you is that the excitation factors and seem to track the amplitude of 2,2, maybe even a little bit of the 2,2,3, but we don't have enough data points really well, which suggests that the source function might be flat for this lower overtones. Yeah. Okay, so this is kind of small, but well. So again, x-axis from and spin. First, and then the different colors are indicating different mass ratios. First plot is showing you the source function for the different parameters. And second and third plot allows us to investigate the time ambiguity, which is plotted on the y-axis. The main feature that I want to draw your attention to here is the relationship between between the time ambiguity factor and mass ratio. So what happens is that as the mass ratio, if you look at fixed spin, only at what is happening to the mass ratio, as mass ratio increases, your time ambiguity factor decreases, and effectively what that means is that QNMs are excited faster. And a way to think about that is that when you have fixed total mass but higher mass ratio, effectively the width of your orbit is smaller, so the radial spread of the perturbation is also smaller, and what that means is that QNMs will, the perturbation will cross the black hole potential faster, therefore exciting QNMs faster. And that same intuition can be applied to understand how the spin is related to the time ambiguity factor. So the idea is that, as you can see, when spin increases, time ambiguity factor decreases. So the idea is that if you have higher spin, then the radial spread of perturbation will be larger. So it's going to take more time for QNMs to be excited. So what I told you today was that to understand the ring down, which has Posner modes as which can be understood in terms of Posner modes according to first order perturbation theory, we can perform an iterative fitting using the variable projection algorithm plus this on-the-go stability analysis that also takes into account the damping time of each Posner mode. And then we validated our approach by looking at several mock waveforms, and we also obtained some physical results by looking at over hundreds of NR waveforms. And that allowed us to explore the physics of asymmetric systems, so high mass ratio, spinning and tail line systems, and also to better understand how the 2-2 harmonic is excited and how that excitation might be independent of the overtone index. And for the future research in ring down in general, it would be interesting to see how different binary black hole systems can be described in terms of QNMs and which other modes can be excited, and also to which extent we can use a model that is only a sum of damped sinusoids and constant with constant frequency breaks down, and how well we can use a model and what is happening close to the peak, and how well we can use that to describe what's happening close to peak. Yeah, that's it. Questions?
Any questions?
I guess to talk about most of the 2-2 modes, I guess are the higher LM modes just not very loud?
They are not very loud, but they're still present. Yeah, they're not very loud, but they're still present.
Okay.
And yeah, that's in our, as far as I know, our code is the only one that allows you to also look at other modes. Because usually people will look at the 2-2 and they find these other harmonics as they appear on the 2-2 because of mode mixing. When you go from spin weighted spheroidal harmonics to a spin weighted to spherical basis, you have to do some mode mixing. Yeah.
So 221 and 222 decay much more rapidly than all the other ones. Is it because they have like higher quadrupole moments and they're radiating more gravitational waves?
Yeah, so 221 and 222 they decay faster than 220, which is like so as the overtone number increases, the damping time they decay faster at a faster rate. So 223 will also decay faster than 222, and so on.
Cool.
So I have a pretty naive question. Can we go back to the Tucholsky equation slide? So how do I see that the solutions to this are not bases? Is there a singularity in this equation or something like that?
Yeah, so, well, there are some ways to think about that. First, these are damped sinusoids and they are sourced at a specific point in time, and they will also decay at some point in time. So you shouldn't be able to model an entire waveform using that, something that is sourced like at some point.
Sure, but so can
So
we go back to-
mathematically, I don't think you can see that mathematically, like at least, I think it's non-trivial.
But can we? So, but
Oh, yeah,
there's
yeah,
no-
we can go
the
back,
fact
yeah.
that the eigenvalues are complex probably. Has,
Yeah, we can go back, yeah. But I don't think it is trivial to see it from the equations.
Yeah, I guess I'm just trying to think about like in a normal Sturm-Liouville operator,
Yeah,
the
yeah.
eigenvalue should be real, right? But so somehow, I'm trying to get some intuition for why this is not normal.
That also has to do with the boundary conditions.
Okay, yeah, that's true.
Yeah. Because we necessarily need to have negative, like complex frequencies that will go to zero at infinity.
Mm.
Otherwise it will blow up.
So, because you're doing nonlinear fit, you need initial guess values for the modes that you're fitting for, right?
Yeah.
So, what do you do for that? And also, do you know how much changing the initial guess affects?
Not much.
Okay.
Not much, yeah. I think we use, right now I think we're just getting like some random numbers within a range, but at some point we're just keeping it fixed at very small numbers. It doesn't change much.
Any other questions? Let's thank our speaker again.
Thank you.